Okay, Assalamualaikum and apa khabar semua? So in this video, I'm going to discuss with you the example that we had in our recorded our live stream class before last week regarding on the balanced three-phase fault. Okay, in this example that we have studied before, we had the fault at bus number 3, and these are the result that we have calculated. So basically, just to recap that our objective for balanced three phase is basically we want to analyze what are the voltage at each of the buses. Okay, we have bus number 1, 2 and 3 here during fault, and what are the current, how much current flowing through all the branches in the network. Okay, so as you can see in this example, in the first case we simulated that for the fault at bus number 3, these are all the current and voltage at each of the buses. As you can see, if you assume that all the buses originally at 1 per unit, okay, and but during fault all the buses, I can see that all the voltage have dropped to a certain value. For example, voltage at bus 1 has dropped to 0.76, okay, bus 2 has dropped, the voltage has dropped to 0.68, and the worst basically the voltage drop is typically at the location of the fault, okay, which is has dropped to more than 70% of the original voltage. Okay, so now let's go on to the next case, where what will happen to the buses if we have a fault, if the fault occur at bus number 2. Okay, so at bus number 2, as you can see, so the first step is basically we are following the same step we had before, just we switch the location of our fault. Instead of bus 3 before, we now try to simulate what will happen to all the voltage at all the buses and how much is the current flowing through all the buses if the fault occur at bus number 2. Okay, so first and foremost, you have to draw the reactance diagram as usual. Okay, you convert everything in per unit. Okay, all the reactance or impedance are in per unit, and you include a line here to simulate that. The switch here basically just to indicate there is a fault occurring at this point here lah. Okay, and the fault also flow through an impedance, a fault impedance, and to the ground. Okay, so after that you draw the Thevenin. If you want to proceed, then because we are now trying to solve the problem using Thevenin equivalent networks, so we're going to change all the diagram here into a Thevenin equivalent. So as you remember that for Thevenin equivalent, you need to short out all the voltage source. Okay, to short the voltage source to ground. Okay, as like this one. Okay, and the rest of the network remains the same. And then other than shorting the voltage source to the ground or the generator to ground, you add another voltage Thevenin at the location of the fault. Okay, and please remember the sign is that the positive terminal is facing towards the ground. Okay, so just add this Thevenin voltage source, and in the end the rest of the impedance, okay, which actually connected into the same network connected to the fault, will be the Z Thevenin, the Thevenin impedance. Okay, all right, so after that you want to find the Thevenin impedance, because the Thevenin voltage is basically, we assume that is a voltage at this bus here, V2, okay, at 0. Okay, so we assume that V2 at 0 is actually the unit is at 1 at the angle of 0. Similar with as voltage 1, the initial voltage 1, pre-fault voltage is 1 at the angle of 0. Okay, as well as voltage 3, the bus voltage at bus 3 before the fault is also 1 at the angle of 0. That is a very assumption lah. Sometimes it might not be a 1 per unit, it might be a different value, so be very careful that you have to read the question very carefully. What are the pre-fault or the voltage before the fault occur? Okay, so we're going to use that voltage later on to calculate the voltage, to estimate the voltage during the fault. Okay, so meaning that if this voltage is connected bus 2, so meaning that the voltage Thevenin also is at 1 per unit at angle 0. Okay, because at the same location lah. Okay, and then you key in the fault impedance is 0.16. make sure it's also per unit. Okay, so now our task is you want to find the what is Z Thevenin, right? Because you want to find the fault current, you need the value of Z Thevenin. So as usual, if you look at this tree network, you can see that this tree it's hard to simplify this without changing this delta configuration into Y configuration lah. Okay, so I'm sorry, I forgot. That's for the first case. In this case, as you can see, the bus number 3 is not connected to any network. So you can see that these two impedance are basically in series, right? It is in series, and these two together can combine them, okay, into one, and is parallel with 0.8. Okay, so if you combine this together, it become J0.4. Okay, the calculation is this one. So you parallel 0.8 plus with 0.4, and 0.4 is this one here, because J0.4 is both are on in series. Okay, you parallel with J0.8 and you get J0.4 per unit, which is this one here. Okay, right. And then okay, but this is not done yet. You have to further simplify it because you only want only one impedance, so you need to further combine. Okay, again, this is the figure from previous slide. So basically, if you look carefully at this figure here, okay, this is basically, you can see that J0.2 is in parallel with J0.4, right? Sorry, J0.2. Now J0.2 is in series with J0.4, okay, and these two are in parallel with J0.4. If you cannot see that, okay, you look at this. Okay, this is a common ground. So basically, a common ground, it basically is connected together lah. Electrically is connected together. So it's like this. It's a ground also, and it's connected to this ground, and this is like a common ground lah. So as you can see in this network, these two are in parallel together, right? It's connected in series, okay, because bus 1 is not connected to anything else, okay, and this branch here, okay, so J0.4, okay, so at this point, the three resistors are connected at the same common point at here and here lah, okay. So basically J0.2 plus 0.4 is in parallel with J0.4, okay, which is this one here. Okay, I hope you can see that. All right, so if you combine them together, parallel them together, you will have J0.24. okay, you have this equivalent circuit, but it is not done yet. Okay, so it is basically the Z Thevenin. Okay, all right, so okay, you calculated the Z Thevenin. Now you want to calculate the fault current, which is what is this fault current here, right? You want to find this value. All right, so the fault current is basically, if you look at the circuits here, it just has basically a two impedance circuit. As you can see that this ground here can be connected, okay, down here, because common ground. Okay, this is also a ground. So it's basically like this. So this is just a switch, doesn't matter, just a straight line. Okay, so it's basically that you have a Thevenin voltage and two impedance in series lah. Okay, so it's very simple. So it's just, so the current is just voltage divided by the total impedance. Okay, the total impedance basically the Z Thevenin and the Z fault. Okay, Z22 here is basically Z Thevenin lah. Alright, so V2 here is the voltage at bus number 2 here, which is the same as the Thevenin voltage here, right? So V20 here is basically the V Thevenin. Okay, so it's 1 at the angle of 0. Okay, at the angle of 0, because or 1 plus J0, the same thing, divided by the total impedance. Okay, and you got the fault current is minus J2.5 per unit. Okay, so now you are done with the first part, which is to find the fault current. Okay, so the next step, if we want to find out what happens to the voltages at the rest of the buses, right? All the buses during fault, as well as what are the current that flow through all the branches. So let's go to the next step. All right, so before we find we calculate the voltage, we need to find what are the current through that flows from the generator, right? Okay, all right, so the first thing is you need to find the IG1 and IG2. This is IG1, G1 is from generator 1, G2 is from generator 2. Okay, so if you can see that IG1 here from this circuit, okay, it flows through this branch, okay, and to the fault, and IG2 also flow to the fault. Okay, so you can calculate IG1 and IG2 using a current divider law, because we know that it's fault current here, okay, you can see that the fault current that flow from out from the bus number 2 is equal to these two current going into this junction here, right? So basically this is basic KCL law at bus number 2 or node number 2. You can say mode or bus, it doesn't matter lah. Okay, all right. So then because of that, and then you can see that these two branches are parallel. See, you can connect this ground together, and basically these two are in parallel lah. Okay, so remember parallel circuit, you can perform current divider rule, right? So for that's why so therefore IG1 is equal to I01. I01 is basically from ground 0 to 1 lah. This is the same thing as from I1 to 2. Okay, all right. So it's J 0.4 divided by 0.4 here. You want to find IG2, we need to divide the opposite impedance divided by the total impedance of the two between how do I get 0.6 here? 0.6 is basically 0.2 plus 0.4 lah. Okay, because this impedance both are in series. Okay, and 0.4 is the same as this impedance. Okay, multiply by the total current, and we got J1.0 minus J1.0. Okay, that's for the current from this branch here. Okay, and similarly we can do the same current divider law for the other branch. Okay, using the same principle. Okay, just now we got the only difference just what is the value of the impedance on the numerator. Okay, instead of 0.4 it's now 0.6. So the total current is minus 1.5. Okay, all right. So and then let's double check with the, remember what the fault current we just calculated here is J02.5, right? Okay, if you look for carefully at the result, then if you combine this together, if you add together, it becomes minus J2. If you add 1.0 plus 1.5, it becomes minus 2.5, which is equal to I2 fault lah, the fault current. All right, so I mean that your calculation is correct. Okay, so the next step after you find the branch current coming from the generator is to find what are the change of voltage from each bus to the ground. Okay, you want to find the change of voltage. So let's take a look. So you have 3 buses, so you need to have 3 change of voltage lah. So delta V1 or the change of voltage at bus number 1 is basically from this side here, from ground to bus number 1. So I think this one is already been explained in this example, previous example for case 4 and bus number 3. Okay, it's equal to the current or the impedance between the ground and bus number 1. Okay, Z01, 0 means ground lah here, multiplied by the current flowing through the impedance between bus 0 and 1. So I01, so Z01 is Z0.2, which is this one here, and I01 is the current you have calculated just now, which is J1.0 here. Okay, you multiply them together, and the change of voltage is 0.2 per unit. Okay, so meaning that during the fault the voltage has dropped by 0.2. Okay, so how about the change of voltage at bus number 2? Okay, similar logic with calculation with bus number 1. The change of voltage bus number 2 is here. Okay, so it's equal to the impedance between the ground bus to the bus number 2, which is J0.4, multiplied by the current flowing through the this branch here, which is IG2, which is this one here, 1.5. We just calculated just now. You multiply them together. Now the change of voltage bus number 3 is 0.6. Okay, now so let's take a look at the bus at bus number 3. Okay, this is the total bus. Bus number 3. Okay, this is a little bit tricky to understand this, but okay, so to find the change of bus voltage bus number 3, we cannot use the simplified network like before, like case number 1, right? Number 1. So we need to use the this simplified network, this network here, the original network, in order to find the change of voltage from bus number 3. Because if you simplify, then the bus number 3 disappear. We don't want the bus number 3 to disappear lah. Okay, so what is the voltage is basically between the ground to bus number 3 here, between these 2 points here, between this point and this point. What is the voltage drop between this the ground point to bus number 3. Okay, so you can see that the change of voltage at bus number 3 will basically cover two impedance, right? Basically will cover this voltage drop from ground to bus number 1 plus, yeah. All right, let me clear this thing up. So to find the voltage drop from ground to bus number 3, basically you have to travel through two impedances, right? From ground to bus number 1, and then from bus number 1 to bus number 3 here, right? So you have the current have to flow through these two impedances lah. Then we can find the voltage drop between ground to bus number 3. Okay, similarly, if you have an example for like this one, like if you have a voltage source and you have a resistance here, resistance here, right? Okay, so what is the voltage from this point to this point? Is a total of voltage drop from this point to this point plus this voltage and plus this voltage, right? So you have three resistors and you have to add up all the voltage drop through all the impedance. Similarly with this case lah, if you want to find the voltage drop between these 2 points, then you need to find what is the voltage drop between 0 to 1 plus the voltage drop between 1 to 3. Okay, so what's the voltage drop between 0 to 1 is delta V1, right? We calculated that earlier here, right? Delta V1 plus now the tricky bit is what the voltage flowing from what the voltage drop from bus 1 to bus 3. Okay, so if you look carefully, let me clear this thing up. Tengok carefully, yeah. So if you look carefully, the current here basically from Ig2 we split into 2, right? Okay, we split into 2. Okay, so remember that the current Ig1 here is equal to minus J1.0, right? Okay, so if the current flow here, it will split into 2, and take a look at this resistor here. Okay, this resistor is at impedance, is 0.8. The branch flowing through this current also, this branch also is 0.8, which is 0.4 plus 0.4. Okay, if you remember from basic circuit analysis, right? Okay, if resistor here is R1, let's say R1 and R2 has the same value, right? Let's say the current here is 10 ampere, right? So if both resistors have the same value, what will be the current flowing through this resistor? It will be divided equally into 2, right? 5 ampere and 5 ampere, right? Kan? Because both are resistor has the same value. So basically you need to perform current divider lah. But in this case, since these two impedance are in these two branch, okay, has the same value, so the current will be divided equally lah. Okay, all right. So but actually we want to find, okay, in this branch here, so the current flowing through this branch and this branch will be minus J1.0 divided by 2. Okay, so this current is which is minus J0.5, and this will also become minus J0.5, right? Okay, so now we want to find what is the voltage drop through between 1 and 3. Okay, so between 1 and 3, the current have to flow through this J0.4. So the voltage drop between 1 and 3 is minus J0.5, which is the same, the current flowing through this branch multiplied by the impedance lah. So basically this one here is minus J0.5. Okay, so this is 0.4, this one. So then if you combine them together, this voltage the voltage drop between this branch here plus the voltage drop between this branch here, and you get the total voltage drop from ground all the way to bus number 3 lah. Okay, so you add up together and the voltage drop is 0.4 per unit. Okay, so this is just basically pure a simple circuit analysis lah. All right. Okay, so the bus voltage during the fault. Okay, so after calculating the change of bus, then the work is now become much easier. So the voltage during the fault is basically the bus voltage before the fault minus the change of voltage during the fault. Okay, since we assume that, okay, the free fault voltage are all 1 per unit and then go 0. Okay, and the change of voltage at bus 1 is 0.2, so you minus them together become 0.8. Similarly for bus number 2 and bus number 3. Okay, all right. So after that, as you can see here, okay, all right, So the short circuit current, you can also calculate the short circuit current by using an Ohm's law. Okay, now you calculated that V1, V2 and V3. You can use this to find the short circuit current, or the current. The short circuit current means the current flowing through this branch during short circuit lah. Okay, so I12 is basically from I1 to branch number 2 here, 1 and 2. Okay, this is I12 is basically V1 minus V2 divided by Z12. Okay, you know that already, you find V1 already. V1 is this one, V2 is this one. Okay, minus together divided by the impedance between them. Okay, this is the current flowing through this branch here. Yeah, similarly for between branch 1 and 3. Okay, and also from branch between branch 3 and 2. Okay, because the current has to flow in this direction. Okay, remember, always draw the fault current direction, okay, at all time lah. Okay, so because you want to know which voltage minus which voltage, and that's very important also. Okay, okay, all right, let's stop for a while, and then I'll continue with second video to analyze what will happen when the fault occur at bus number 3. Okay, I'll see you back.